Hello, in this video I'm going to talk about diffraction gratings, and this is the key bit of equipment that opens the door to allow us to understand the different types of star that exist, classify different stars, and then move into talking about how stars evolve. So if you think about what it's like when you just go out and look at stars in the night sky, we can't even say basic things about whether they're bright stars or not. I mean, you look at a star that seems quite bright in the sky. Well, is that a fairly bright star that's close, or a very bright star that's a long way away? Even basic stuff like that, we can't really say. Now, we need more information from the starlight that we're receiving from stars, and diffraction gratings give us that, because what they do is they split out the starlight into a profile of intensity as a function of wavelength. So this is called a stellar spectrum, and it's splitting the light out and giving us loads more information, because we're going to look at stellar spectra in more detail in another video, but just as a sort of basic difference that you might get on it, a very hot star is going to have lots of short wavelength photons because they're the high energy ones. So you might get a basic profile that looks something like that, where we've got a lot of short wavelength photons, so lots of intensity at these shorter wavelengths. So that might be for a hot star. You might have a cooler star, which might look something more like that, where you've got more sort of middling wavelengths, certainly move to longer wavelengths in terms of where the peak is and the overall distribution. Of course, it's also going to give us information of the area underneath these graphs, particularly if we can work out the distance to the star. It's going to tell us about the power output of that particular star. So there's a lot of information that we've got here, and we see that there's more information as well, because there's going to be little signatures in these spectra which then tell us what elements are in the star as well. So this is all stuff that we can unpick when we look at the details of a stellar spectrum. But it's diffraction gratings that are allowing us to do this, and they're put inside these instruments called spectroscopes. Sometimes you can just use a straight diffraction grating, which I'll get onto later. But spectroscopes are diffraction gratings with a bit of fancy kit around it in order to do all of this splitting out of the light and then processing it all. And it was early 19th century, Joseph von Fraunhofer, who came up with these, and that's what set us on this path of understanding the different types of star. So how do these diffraction gratings work, and what sort of types of diffraction grating are there? Well, you get reflective gratings and transmissive gratings. So the reflective ones, as it sounds like, the light is coming in and then it's bouncing off, and it bounces off a sort of sawtooth surface that you get. The size dimensions of these teeth are optimized to a particular wavelength of light that's coming in, but you get a reflection of the light off of these teeth, and they end up interfering in certain ways and producing an interference pattern. You also get, which are the ones we'll look at with a little bit more detail, what are called transmission gratings. So transmission, the light's going straight through. They've got similarities to what we did back in the waves topic on Young's double slit. So instead of just having two slits, and you've got light coming in, or whatever wave coming in, but you've got waves coming in and then they diffract at these slits, and then you get an interference pattern on a screen. This is more or less what we're doing, but beefed up to thousands of slits. So we haven't just got two slits. In a transmission grating, you might be getting 1,000 per millimeter. And this is slit. When it comes to a transmission grating, we're talking about slits in inverted commas here. They're not necessarily actual gaps. We haven't cut through a surface in order to create these actual slits. You're really setting up changes in refractive index of the material that the light is passing through. So you might get a sandwich with some gel. So you've got some gel being held in place, and you can score this material with lines. You actually cut lines into it, and it's changing the refractive index. And that variation of refractive index then acts as a slit, which is going to diffract the light that's coming in. So if we've got loads of these slits, we've got the same principle that's operating. You know, when we were looking at 2 points that were then diffracting, we're drawing our wave fronts like this, and they're interfering with each other. And then we, you know, from the just drawing off of these wave fronts, you've got the useful way of saying, right, well, if we connect these ones, that gives us one way that the wave is moving off. It's going to move off this way. So that's our passing straight on wave, which is going to give us our central peak. And then we've got waves which are going off to the side. Like if we connect this wave front to that wave front, I should have done that in a different color. Let's draw that line in blue. So if we draw that line down, then you can see that's moving now in a different direction. And that's going to head off to our next maximum. So we're going to have another maximum over here. So that's how we're building up this diffraction pattern using the grating. And the direction that these waves are going to be moving in, the direction to each peak, is a function of wavelength. So that's how we're getting this variation of intensity with wavelength. This is how we're unpicking this and actually seeing intensity as a function of wavelength, because we're going to have, you know, the blue peak, the first blue peak will be, you know, maybe here, and the red peak will be over there. It's going to vary by wavelength. So the longer the wavelength, the more it's going to diffract round. So because we've got loads and loads of slits, we're getting a much sharper and brighter interference pattern. More slits means we're letting more light through, and it also means that we're getting much more resolution in the interference pattern. And I'll show you some of those interference patterns in a minute. Let's do a little bit of maths first of all on this. So say we just have these 2 slits. So we've got the usual thing of the distance between these slits is some distance d. So we've got slit Q, we've got slit P. This is then going off, let's draw our red lines in, going off to some maximum, not the central maximum, but somewhere off somewhere else. That's our straight through that we've got. And we've got some angle theta here that this new diffraction peak is off at an angle theta to the center. Now let's then drop in a perpendicular. You know, we did all this in our double slit before. You drop a perpendicular in, and that's fine, providing we're saying that d is, you know, much less than the distance off to the screen that we had before. So providing we've got a small gap between these slits, we can drop that in. Then we're saying that this angle here is going to also be theta, which is fairly clear from the trig. If that is 90 degrees, then this angle here is 90 minus theta, so this angle must be theta. So we can say that sine theta is equal to opposite over hypotenuse. So it's going to be equal to this length here, which let's call that y, divided by the hypotenuse being QP, so divided by the distance d between the slits. Now, what is y? Now, remember what's happening here. If we're going off to a maximum, then that must be an integer number of wavelengths in order to get constructive interference and produce a maximum. So y has to be an integer number of wavelengths. So that gives us our diffraction grating formula of sine theta is equal to n, 0, 1, 2, 3, etc., some integer, times the wavelength divided by d. That's our diffraction grating formula. Or written another way, sometimes you'll see it written out as d sine theta is equal to n lambda for n equals 0, 1, 2, 3, etc. And yeah, you can see off of this then that if we've got a shorter wavelength, looking at this one here, sine theta is n lambda over d. Well, n and d, so for a particular maximum, say the first maximum, we'll say n is equal to 1, d is fixed. So for shorter wavelength, we're going to have a smaller sine theta, so we'll have a smaller angle. So shorter wavelength will diffract off less than the longer wavelength. So that's what we're going to see. So when we then look at the diffraction pattern that is produced, you'll have blue towards the center, that's our central star, and you'll have red further away from the central star. And you end up seeing things that look like this. So at the top picture, this is just a simple diffraction grating that you can buy for, say, 20 quid and stick onto an eyepiece on a telescope. So you've got your central peak here, which is the star. You know, if you've got light which is just going straight through, well, you're just going to get an image of the star. So that's our central peak. This is then our first peak on the diffraction pattern, where we've got blue on the inside, and then it's going through to red on the outside. And then if you extended this further off to the side, you then see another one of these sort of streaks of going blue to red, and it will just keep on going off further and further to the side. They'll start overlapping, and you don't really want to look at these subsequent patterns anyway, because the brightest one is the first one, so you might as well work off the one that's got the most information in it. If you then process this, even off of this £20 diffraction grating, you can get something that looks like that, and that's just doing some simple processing, just using paint on your computer. I mean, it's not high-tech processing, but you can already see that we've got patterns appearing here. You know, we've got dark lines appearing. You know, we've got a dark line here. We've got them over here as well. So there's a lot of these. You've also got brighter bits. So there's a lot of information which is in there that can then be analysed. So it's not only telling us the distribution of the intensity, just as a smooth distribution, you've got structure inside it as well. So there's two things that these stellar spectra are telling us: what's going on with this smooth distribution, and then what's going on with the structure inside that smooth distribution. That's what I'll talk about in the next video. If you've got a better bit of equipment, then you'll get something like this bottom picture here. So you've got a much sharper spectrum there. Yeah, you can see these dark lines, these what are called absorption lines, are much more sharply defined. And then it gets converted into this sort of shape. So this bottom graph here, you'll see we've got wavelengths along the bottom here, going from short wavelength here, 400 nanometers at this end, up to, well, 600, 700 nanometers at this end. So you've got wavelength on the x-axis. On the y-axis, you've got intensity. So how much light are we getting at each wavelength? So you can see we've got a similar setup. Even this rough sketch that I've just drawn here has got similarities to this. So you can see we've got this general shape. Yeah, we've got this general distribution. Okay, that went a bit wonky. Yeah, which is going up and then it's coming down. That's our general shape. And then inside that general shape, we've got these absorption lines. We've got this structure, which, as it says here in the picture, is telling us things about the hydrogen and the state of the hydrogen in the star. So there's a lot of information packed into stellar spectra, but without diffraction gratings, we can't get hold of it. So that's why they're so important, and they're just fundamental bits of kit to the astronomer. So as I say, next video, we then need to start taking a closer look at these stellar spectra. So what is each bit telling us? What's the continuous bit telling us? And what are all of these absorption lines, and then in some cases emission lines, telling us about the structure and composition of a star?